Hello, everyone. We are now in Module 3, and we will continue our discussion on the second law of thermodynamics. We will start with a review of the first law, defining some terms, and see how important the second law is. So recall in first law, this includes energy and different ways to transfer, like heat and work. It sets rule on how energy is being transferred. Just to give you an overview on what to expect for the second law, so we will start more with the concepts. What do we mean when we say direction of spontaneous change? And we will introduce a new state function, which is entropy. Now, in terms of the limitations of the first law of thermodynamics, when energy from the system is transferred to the surroundings, no energy is lost in the process. Energy lost in the system is gained by the surroundings. However, the first law does not give us any sense of direction. While first law sets up possible processes, it does not tell us which is the most probable or which actually does happen in a given set of conditions. While first law tells us that reverse process could happen, it doesn't tell us the direction in which process are spontaneous. Example, if we will be considering an ice that melts into water at room temperature, we could say that process is spontaneous because water at room temperature cannot go back to its original state ice, and that process is considered to be a non-spontaneous. Considering the first law here, energy is conserved. However, only one direction is spontaneous. The first law does not give us the direction of spontaneity. So recall that in first law of thermodynamics, it states that the total energy of the universe is constant. It is useful in keeping an account of heat and energy balances. However, it does not. It makes no restriction regarding the direction of the spontaneous change that a system can undergo. And if we will only be considering the first law, it is impossible to explain the process that I mentioned earlier. So thus, it limits and it shows the need for a second law. The second law of thermodynamics asserts that processes occur in certain direction. And energy, not only it has quantity, but also energy has a quality. The nature of the second law experience shows that there's a natural tendency of a system to proceed toward a state of equilibrium. So, for example, when a hot object is placed in contact with cold object, the temperature of the two objects become equal after some time. And when two bulbs containing gases at different pressures are connected, the pressure in the two bulbs become equal after some time. Now, the second law leads to a state function entropy. So this quantity was introduced by Clausius and Kelvin in the 1950s when they formulated the second law. It was given the name entropy, which comes from the Greek word meaning transformation. The second law of thermodynamics leads to a deduction of a state function, entropy, that for isolated systems, the equilibrium position corresponds to what we call maximum entropy. Now, before we focus more on the entropy, it started with the development of what we call cyclic heat engines. The cyclic heat engines were developed during the Industrial Revolution. So example, when people burn coal and then they boil water, and the steam that is being produced were used to drive piston, thus to produce mechanical work. The cyclic heat engine converts heat to what we call continuous mechanical work. And this approach was initially demonstrated by Carnot in 1824. The second law was formulated by considering a heat engine that is able to carry out work continuously. Now, if a heat engine, if we will be picturing this in a molecular level, heat in flows into the system, thus increases the molecular motion. Rather, it increases the random molecular motion. And then your system here produces work, which if we will take it in a molecular level, this is in an orderly molecular motion. So in a heat engine, the working substance, example, steam absorbs heat at high temperature, QH, and expands, causing a piston to move and produces mechanical work. Now, if we will be considering the engine to operate continuously, it has to be restored to its original state so that it can expand again and produce work. Now, this can only be achieved if the working substance loses heat. So to solve or to determine the efficiency of an engine, efficiency is equivalent to the work done by the engine all over the heat input. Now, considering an isothermal reversible process. Now, if we will be looking here in the PV diagram, so volume, which undergoes expansion, increases volume from V1 to V2. So expansion, in expansion, maximum work here is done by the gas. Since the process is cyclic, delta U is equal to 0, which is equivalent to Q plus W. Since Q is equal to negative W, the formula for the work, reversible work during expansion as it expands from V1 to V2 is equal to negative nRT ln V2 over V1. Now, since this is reversible, we will be considering the compression, which is the minimum work done on the gas. And reversible work is equal to negative nRT ln V1 over V2. So thus, the work here, which is the sum of the reversible expansion plus reversible compression, work net here becomes 0. Now, second law here, it explains that since the formula for the efficiency, work done by the engine all over heat input, from the equation earlier, we could say that it is impossible to get 100% efficiency. So this is also studied by French engineer Sadi Carnot, which shows that for an engine to produce continuous mechanical work, it must exchange heat with two bodies at different temperatures. So from the equation, heat input is equal to work plus QC. So work here is equal to QH minus QC. So this just explained that for the cyclic heat engines, it is impossible to get 100% work since there's a heat loss in the system. Another statement of the second law of thermodynamics is explained by Kelvin Plan. So it is impossible for a system or substance to undergo a cyclic process whose sole effects are the flow of heat into the system from a heat reservoir and the performance of an equivalent amount of work by the system on the surroundings. Another statement of the second law is by Clausius, which states that it is impossible for a substance to undergo a cyclic process whose sole effects are the flow of heat into the system from a cold reservoir and the flow of an equal amount of heat into a hot reservoir. So if we will summarize this part A, the second law of thermodynamics introduces a new concept, which is entropy. In the next lecture, we will be considering the Carnot cycle.